Welcome to Chapter 5. As a radiation safety officer, your eyes and ears in the facility are your radiation detection instruments. You cannot see, smell, or feel ionizing radiation. So, you must rely entirely on your equipment to ensure safety. This chapter is vital for your RSO examination because it moves from theory into the practical reality of how we find lost sources, measure a worker's exposure, and verify that a room is safe for the public. We will explore the different families of detectors, gas filled, scintillation, and personal monitors. And more importantly, we will learn why picking the wrong tool for the job can lead to dangerous safety errors. Principles of gas fill detectors. Let us start with the most common family gas fill detectors. Imagine a simple metal can filled with air or a special gas. In the center, there is a wire called the anode. When radiation, like a gamma ray or beta particles, passes through this can, it crashes into the gas molecules and knocks electrons off them. This creates a cloud of charged particles. By applying high voltage to the center wire, we pull those electrons towards it. This movement of electrons create a tiny pulse of electricity. The strength of this pulse and how we count it depends entirely on the voltage we apply, which brings us to the different regions of the detector operation. The ionization chamber region. The first stop on our voltage curve is the ionization chamber region. At this relatively low voltage, we simply collect the electrons that the radiation knocked loose, nothing more, nothing less. Because the electrical signal is directly proportional to the total energy the radiation left behind, these meters are incredibly accurate at telling us the dose rate. If you need to know exactly how many milliroentgen per hour are in a room, you reach for an ionization chamber, like the famous cutie pie. However, because there is no signal amplification, these meters are not very sensitive. They won't click for a single particle. They are best for measuring high intensity radiation fields. Proportional counters. If we turn up the voltage, we enter the proportional region. Now, the electrons are pulled so fast that they crash into other gas atoms on their way to the wire, knocking more electrons loose. This is called gas amplification. It is like a snowball effect. Crucially, the final signal is still proportional to the initial radiation energy. This allows us to distinguish between different types of radiation. For example, a heavy alpha particle creates a much bigger snowball than a tiny beta particle. RSOs use proportional counter in the lab to identify what kind of contamination on a surface. And when specialized with BF3 gas, they are our primary tool for detecting neutrons around high energy linear accelerators. Geiger-Müller survey meters. Now we come to the most famous meter, the Geiger-Müller or GM counter. Here, the voltage is so high that even a single tiny interaction causes a massive avalanche of electrons along the entire wire. It is like a hair trigger on a gun. Once it is pulled, the whole thing fires. This makes GM meters incredibly sensitive. They are the police dogs we use to sniff out tiny bits of spilled radioactivity. If you hear a GM meter clicking, it means it found something. But remember, because every pulse is the same size, the GM meter cannot tell you the energy or the type of radiation. It just tells you something is here. GM counter limitations, resolving time. There is a catch to the GM meter's high sensitivity, resolving time. After that massive electron avalanche, the meter needs a split seconds to reset itself. During this dead time, the meter is blind. If you walk into an extremely high radiation field, the particles might hit the meter so fast that it never has a chance to reset. The meter gets jammed or saturated. For an RSO, this is a nightmare scenario. You could be standing in a lethal radiation field, but your GM meter is reading zero because it is paralyzed. Always approach a high dose area with an ionization chamber, not just a GM counter, to avoid this trap. Scintillation detectors, solid state. Not all detectors use gas. Scintillation detectors use solid crystals, most commonly sodium iodide. When radiation hits these crystals, they scintillate, which is just a fancy word for glowing or flashing. A special tube called a PMT sees that tiny flash and turns it into a large electrical pulse. Because a solid crystal is much denser than gas, it is much more likely to stop a fast moving gamma ray. This makes scintillation detectors extremely efficient. They are used in your gamma cameras and PET scanners to create images, but RSOs also use handheld version to identify unknown isotopes by looking at their unique energy fingerprints. A specialized instrument, the dose calibrator. In every nuclear medicine hot lab, you will find the dose calibrator. It is a large, deep ionization chamber used to measure the curies or becquerels in a syringe before it goes to a patient. As an RSO, you are legally responsible for its quality control. You must check consistency every single morning to ensure the meter has not drifted. You must verify accuracy once a year. You must prove linearity every quarter to show the meter works at both high and low activities. And finally, you must check geometry to ensure that the same amount of activity reads correctly whether it is in a tiny vial or a large syringe. Personal monitoring, the film batch. Now we shift from measuring the room to measuring the person. The oldest form of monitoring is the film batch. It contains a small piece of dental style X-ray film. The more radiation you receive, the darker the film becomes when it is developed. We use different metal filters inside the batch to tell if the dose came from a soft beta particles or a hard gamma rays. The big advantage is that the film itself is a permanent physical piece of evidence, a legal record of your exposure. However, they are fragile. If you leave your batch in a hot car, the heat will ruin the film and give a false reading. Thermoluminescent dosimeters. A modern choice is the TLD, thermoluminescent dosimeter. Instead of film, it uses tiny lithium fluoride crystals or in India, calcium sulfate dysprosium crystals that trap radiation energy. When the crystals are taken to a lab and heated, they release that energy as a flash of light. The brighter the flash, the higher the dose. TLDs are wonderful because they are very small, perfect for the ring batches that nuclear medicine technologists wear to track the dose to their fingers while handling syringes. They are also much tougher than film batches and are not affected by humidity. Optically stimulated luminescence. The current state of the art in personal monitoring is the OSL badge. These are similar to TLDs, but instead of using heat to read the dose, we use a laser. This is a huge advantage for the RSO because OSLs can be reread multiple times if reading is ever questioned, whereas hitting a TLD erases the dose forever. OSLs are also incredibly sensitive, detecting even the tiniest trivial doses. They are the standard whole body batches in most modern hospitals today. Immediate readout, pocket and electronic dosimeters. You cannot wait a month for a lab report. You need to know your dose now. For this, we use direct reading dosimeters. The old style is a pocket chamber that you look through like a telescope to see a moving needle. The new style is the EPD, a digital paper that beeps and flashes if you get too close to a source. As an RSO, you should issue these to anyone performing a planned special exposure or to visitors entering a high radiation area so they can walk out the moment they hit a preset limit. Instrument calibration and pre-use checks. Finally, let us talk about maintenance. A radiation meter is only useful if it is working correctly. The law requires every regulatory instrument to be sent to a licensed lab for annual calibration. In India, it is for 2 year period. Every 2 year we have to send regulatory instruments to a licensed lab. But your job does not end there. Every time you pick up a meter, you must perform a pre-use check. First, look at the sticker. If it is out of date, pull it back. Second, check the battery. Third, do a source check by holding the meter up to a small known check source to make sure the needle actually moves. If you follow these simple steps, you ensure that you are never walking into a hazard with a broken eyes and ears. Summary of Chapter 5. To summarize Chapter 5, if you are looking for a tiny spill on the floor, grab a GM clicker. If you are measuring the dose rate from a therapy patient, grab an ionization chamber QT pipe. Use TLD rings for your hands and OSL batches for your body. And never forget that the dose calibrator is the foundation of a patient safety in your clinic. Understanding these tools is not just about passing your RSO exam. It is about building a culture of safety where every measurement is trusted and every worker is protected. Good luck with your studies.